Next, we're going to move on to covalent compounds, electronegativity, bond polarity, and we'll take a look at some periodic table relations. So first of all, we look at this one. We see that covalent bonds are sharing of electrons between two nonmetals. They have the goal of becoming like a noble gas, but they do it via sharing electrons. Molecules, these are actually molecules, so covalent compounds are molecules, and we will find them as individuals. Like a water molecule, we can find an individual H2O. But they also will actually join together. In fact, not commonly, but the covalent compound can also form a 3D crystal lattice, and that forms our strongest material we have for us today, which is the diamond. So they can actually go and do that as well, just like ionic compounds. Not as common as them, but they can. Covalent compounds in general in relationship to our ionic compounds have weaker intermolecular forces, and these are the forces actually holding things together. Therefore, because they have weaker intermolecular forces, we'll find that they have low melting points. We commonly buy them. They'll be in a solid, the solid state. You have to be careful because it will melt very easily, or we get them in liquid or gaseous state as well. Covalent compounds are generally not good conductors when it comes to conducting electricity. Types of bonds, we talk about this single, double, and triple. Just remember that a bar, now we're going to start using bars, covalent compounds, because we're sharing them, and that's what the bar implies. Every bar accounts for 2 electrons. A single bond is one shared pair of electrons in. So I have 2 hydrogens, they come together, they want a full octet, so they share their electron. In this process, I have, again, each hydrogen is acting as if it has 2. Double bond is now 2 shared pairs. Oxygen comes as an example of that. Both oxygens say, you know, we have 6, we need 8. Why don't we share 2 of ours? Share one pair and then share a second pair, and they form what they call a double bond between them. Again, acting as if they have a full octet. A triple bond is now 3 shared pairs, and so both nitrogens come into play, and they say, well, we have 5, we need 3 more. Why don't we share our 3? And they form what we call a triple bond. And then each of them again forming a full octet. And now we have that full octet. Remember, the full octet, looking at just one of them, every bar represents 2, so you have 2, 4, you have 6 here plus 2 there. You have, again, 8, and then you have 2. Remember, hydrogens are exception to the rule. It does not want 8. It does not want a full octet. As we go on then down to bond type, we see that the bond type, relationship here, we see as the bond length going from a single to a double to a triple bond. So a single to a double to a triple bond, we see that the bond length decreases, which is expected. But as the bond length decreases, the actual energy decreases. In other words, as they get closer and closer together, they get stronger and stronger and stronger. Going from a single to a double to a triple, we're actually getting closer and closer together. So we document that. We'll actually say that as the number of bonds increases, the bond length decreases. We have an inverse relationship. Or as the number of bonds increases, so does the bond energy. Therefore, we call that a direct relationship. And when we talk about nature, why don't we actually, with fertilizers, why don't we have just plain nitrogen in fertilizers? And we realize, again, because of triple bond. And again, nature, plants just can't break that triple bond. So when we give them nutrients, like the nitrogen, we'll put them in compounds that are in a single bond, making it easier for nature to be able to break it down, pull the nitrogen from the actual substance. Electronegativity, by definition, is the ability of an atom to attract a shared pairs of electrons. Elements with a high, and we didn't do this, EA is electron affinity. It means that accept electronicity or love for electrons, electron affinity. IE is ionization energy. These are both cousins to electronegativity. Therefore, they all act the same. They all increase in the same way. They increase up going up any column and to the right along any row. We'll say that's their trend of increasing. Electronegativity is a relative concept, therefore there are no units, and they're all relative to each other as elements. And so the actual highest number they get to is a 4.0, but there are no units with it. And again, here's our chart of electronegativity. We see as we increase going up and then to the right. That's where we see our increase in this process. General trend. Again, the highest electronegativity, you look up here, usually our noble gases do not have one because they do not want to attract. We will find that down lower they will. They largely they can. But those are the highest ones. The king of the hill is fluorine at 4.0, and the lowest one down here are the cesium and francium. They have the lowest electronegativity. We're moving into bond polarity. Bond polarity, basically, we have three types of bonds. So we're going to realize that covalent can be really broken down. Covalent is really can be broken down to nonpolar and polar. We've talked about that. We also understand that the ionic and covalent aren't enemies, they're actually working together. So the first type we're going to talk about is nonpolar covalent. It is purely covalent. It is actually sharing the electrons equally. This is the only time you will get 100%. It's 100% covalent and 0% ionic. That's the only time you'll ever get that. The highest you'll get when you get to an ionic compound is 80% ionic, but it's still 20% covalent. So we're going to see a lot of our compounds are really gray area. They're either ionic, they're a combination of ionic and covalent in that process. So unlike what we've always been kind of taught, we've gone through this, it's either ionic or covalent. So when we work with bond polarity, we subtract their electronegativities, and the type of bond is all based upon the answer. So if their difference electronegativity is 0, like we see with all of our diatomic elements, we see with Hopwinkel. So remember Hopwinkel: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Remember, they're all diatomics. Those are our Hopwinkels. All of those will have a difference electronegativity of 0. It's just itself minus itself. So you don't even have to actually look those ones up. So we see here hydrogen weighs in as both. Hydrogen has electronegativity 2.1. We have that on our periodic table. So 2.1 minus 2.1 is 0. So a difference electronegativity means it's truly nonpolar. And we see this because electrons are being shared equally on both sides. That's our first type. Second type, still covalent, but now it's polar. And what happens now is they're sharing electrons, but the key is they're starting to share them unequally. And so someone's starting to win, someone's starting to lose. In the process, you have difference in electronegativity. When someone loses, they become positive. When someone gains, they become negative. So it starts to become lopsided slightly. So this is anywhere ranging from 0 up till 2.0. Greater than 0, but less than 2.0. We fall in this category. So we see this with HCl. Hydrogen is 2.1, chlorine is 3.0, 3 minus 2.1 is 0.9, so greater than 0, less than 2, it falls in the polar category, so we draw it out this way. Now with a polar, we draw a polar arrow. The polar arrow always goes towards the element with the higher electronegativity, so it'll always move in that direction. So it has a positive side on one side and moving, it shows you the direction it's moving. So I will draw a polar arrow here, and I will draw a polar arrow on the compound. I only draw it with a polar molecule. Not nonpolar, not ionic. We only draw a polar, which we call a polar arrow. And what happens here is my hydrogen is actually losing, becoming partially negative or partially positive, and again partially negative. So these signs are playing partial. It's not a definite positive, it's not a definite negative, it's a partial because it hasn't completely lost the electrons in that process of transition. We then move on to our third type, and now we finally make the change. We call it ionic. And the ionic is because it's finally greater than 2.0. We call it the 2.0 rule. And in a situation like lithium fluoride, we saw that lithium, again, the difference here is greater than 2.0. Therefore, lithium, cation, the fluoride anion, and we see that they're actually coming together, and actually they're not overlapping, not sharing. There's no overlapping occurring here. They go up to each other. They touch each other. It's our electrostatic force. It's the positive and negative attraction. So that's the electrostatic force in that situation. So down below here, we then just took a look at different types. Well, really quick, just know again, covalent still present. It's just hit that finally it came so strong that the non-metal finally gained the electronegativity. Non-metal finally gained the electron because it has a higher electronegativity, and there's enough of a difference that actually took place. Covalent's still there, but ionic now has taken the lead. So if I was actually to practice this, we look at, for example, potassium 0.8 and fluorine 4.0. The difference is 3.2, so we call it as ionic. And again, these values are given to a chart on your periodic table. So hydrogen is 2.1, bromine, it's a 0.7, I call it polar. I don't even have to look at bromine, Br2, it's diatomic, therefore I know it's going to be 0 and nonpolar. When I looked at H2S, it's going to be the same shape as H2O. We'll take a look at it, but I'm only actually looking at a hydrogen and a sulfur, so get rid of the 2. I'm actually looking at it as one of them. I say the difference is 4.0, it's polar. And then cesium and chlorine. Cesium weighs in at 0.7, chlorine is 3.0, the difference is 2.0, so I classified it as ionic. Remember, ionic, it's ionic, but covalent is still actively taking part in the bonding. So we will actually draw this out here. We have a table here. We realize that um, if I see this, I am in this situation, I'm 0% ionic, but once I get to 80% ionic, I'm still going to be 20% covalent in this situation. So the only time you're ever 100% is when you're with the 100% covalent and 0% ionic. That's the only time. When we break down our types of bond, we have nonpolar, that's a 0. Anything falls greater than 0 but less than 2 we call polar, and then greater than 2 we finally call it ionic. So these are 3 types of bonds we're going to now get specific about. Remember, nonpolar and polar are both still a type of covalent. As we move forward, misunderstand that. We're going to start, I will actually refer to them as polar and nonpolar.